So in this video we're going to look at different types of controllers. So the idea is that we want to make sure that we pick the right tool for the job. So just I got a couple graphics here. If you see, obviously you got a flat tire. You could maybe try to change it using a pair of pliers, but obviously that's not going to be very practical. A lug wrench would obviously be the better tool for the job. So when we're looking at different types of controllers, keep that same sort of concept in mind. So we'll look at several different objectives here. We'll look at the terminology, code execution paradigm, timing issues, and various different types of controllers. So a controller for this class, we're basically talking about a computer-based controller. But in general, it's a device designed to perform control of a system. So it could be electronic, it could actually even be some sort of analog control, just to perform what you need it to do. So when you're talking about the different types of controllers, there's two major paradigms of code execution that could be done. The first one is what they call dedicated code. This is where you write a program and that program is going to run on the controller. And if you need to make a change to that, then you're going to have to stop the entire program and reload it with the changes. On the other hand, we could have something running a base operating system. So if it's running a base operating system, what that means is that you can actually have multiple separate tasks running. So if you need to make a change to one, you could shut down and restart that one with the changes without affecting the others. And there's pluses and minuses to both of these choices. One thing I want you to keep in mind, we'll talk a lot about, is execution timing. So whatever controller that you choose, you need to make sure that it can perform the task in a timely manner. So if you look, for instance, here on this graphic, we have this tank that, there's a pump that was pumping antifreeze into the tank. There's a sensor at the top of the tank, and somewhere you have a controller that's reading the sensor. And when the sensor says the tank is full, the controller is supposed to shut off the pump. But if this is delayed, if this message from the sensor is delayed for some reason, then obviously it's not going to shut the pump off, and then you're going to have, antifreeze overflowing, which is obviously not a good thing to have. So you can't have a controller that just wants to go off and sit there and just give you a little circle sort of thing to watch or whatever, like some of the current operating systems love to do, and you're just like, well, what's it doing? In this case, if it's just going off into la-la land, you've got a mess. So when you look at the different types of timing for programming a controller, number one, you have sequential. Sequential, you just have task 1, 2, 3, 4, 5, 6, 7, however many tasks you have, you run through them all, and when you get to the bottom, then you come back up to the top and you start again. So it's very sequential, the timing is pretty much consistent all the time. Another method is what they call event interrupts. In the case of event interrupts, what happens is that, like, say in this case where the sensor says the tank is full, what it does is it causes a interrupt into the control program, and then the control program's like, oh, hey, the tank's full, let's stop and go take care of this, let's go shut off the pump. on the one hand, in some ways that's more efficient because the controller can be doing other things. But on the other side of that is it's like, okay, well, now all of a sudden it stopped everything else to go take care of this interrupt. And so that may be causing something else to be overflowing or going off. So your timing is not as consistent with event interrupts. And then, of course, there's what I like to call real time. Okay. So, real time tasks are required to be completed in a designated time. So, you can do real time with either one of these, although typically real time is always done with sequential because, again, the timing is more consistent and easier to guarantee that it's done. But again, if it's not done in real time, meaning that it's done, without any delays, that within so many seconds it's going to be done, then you might have a issue like this overflow. There's lots of different classes of controllers. There's what we call just little system on a chips. Okay, so I don't know if I can show you this here. Right here is just a little chip. This is made by a company called Microchip. They make these controllers, and they are relatively cheap, just a few bucks. They have a lot of I/O on them. They have a lot of capabilities, and you can just build them and put them in a circuit that you want. There's various different programmable devices. There's single board computers. There's, of course, just ordinary PCs. And then there's industrial class PLCs and hybrid devices. So let's take a look at each one of these. All right, so this is the PIC Microchip block layout that I just showed you. These types of controllers have dedicated code, so they're a dedicated code paradigm. They can be 8-bit, 16-bit, 32-bit processors in there. They usually run a RISC type of processor with just a few instructions. And they have lots of various I/O. So if you look at this, we have analog to digital converters, we have pulse width modulation modules, we've got digital I/O, we've got various serial communication methods, we have built-in timers. Now that there's just lots and lots of these different models that are made by Microchip. They have probably easily over 100 different chips that you could choose from, and so they'll have different amounts of actual I/O and stuff. So you just have to pick the ones that have what you want. But they allow you to build a circuit relatively cheaply, and they have what they call a watchdog timer, which kind of helps in case something goes wrong. Lot of different features for these. All right, so here's a circuit that I actually built to control the charging and discharging of lithium-ion cells. And so you can see the microchip sitting in here, and then I just have a few resistors just to limit the current through the LEDs. So I had like several different LEDs to tell me the status, whether it was charging, discharging, or sitting idle. A couple of capacitors in there, and that was about it. So fairly easy, something I just kind of put together to test charging and discharging of lithium-ion cells. All right, so this is the chip that I showed you here, the 16F876 one, and it just shows you the different digital inputs and outputs on the chip here. Again, if you go to microchip.com, They have literally hundreds of different ones to choose from. Obviously, some have more features, some have less, and that'll affect the price. But very cool little chips. Then we have what we call programmable devices. Okay, and these programmable devices, there's basically three major ones. There's a DSP, digital signal processor, programmable logic device, and field programmable gate arrays. And these ones are really allow you to do some really amazing stuff very, very fast. So if you look here, this is actually a soundboard. This one here is called the Midas M32. And this board has been out now on the market for, let's see, over 10 years, close to 15 years, I think. And it can simultaneously mix 32 input channels plus another 8 auxiliary channels. So technically it can mix 48 channels. It can provide built-in compression and equalization on each one of those channels. And it does it all in real time. Now this is for obviously for mixing music, and it's extremely important when you're mixing music and that everything is in sync, right? So you have a guitar player and a singer and a drummer, and so you have all these different things going on, and they need to be in time. So if one of these was delayed, that could very easily destroy a song. So using an ordinary PC, you would not be able to mix this many channels together. They just, it might be working fine for a while, but then all of a sudden it's like, oh, I'm going to just take a few seconds here to think and give you a little circle to go around, and now all of a sudden your music is out of sync. The M32 actually is built using those DSPs, digital signal processors. Okay, and again, this is really kind of what they kind of consider old technology here, because it's been around, but it can convert the signals to 48 kilohertz digitized data, and then mix that data. Again, mix 40 inputs into over 30 separate outputs. Okay, so we're not just mixing these 40 inputs into one output. We're actually mixing these 40 inputs into the possibility of 30 separate outputs. They have multiple different buses that allow you to generate lots of different outputs. So it's you might be able to mix these 40 channels coming in with a PC for one output. It's maybe a stereo output left, right. But to actually give you 30 different mixes from 40 different inputs, that's when you think about the amount of data that has to process without any delays, that's very critical. Newer model board here, this one here is what they call the Avantis board. And this one can actually do 64 inputs at 96 kilohertz. So this one here is actually, at least twice as fast and more channels than the 32 one. This one's a lot newer board. This one's only maybe 5 years old. But this one uses that FPGA technology. And so again, it can do something like 25 billion operations per second, converting 64 inputs into analog, or analog inputs into a digital at 96 kilohertz, and then mix those for 42 outputs, and then output those 42 individual outputs. All right, let's take a look at some single board computers here. So single board computers controllers, excuse me, single board controllers. So we have single board computers and controllers. Here we're talking about the controllers. The controllers, the difference is a controller is basically uses that dedicated code paradigm where you create a program and then it runs that program. There's lots of these, very low cost. Okay, you may have heard of or even played with some of these. There's what they call the Arduino. The Arduino is probably one of the earliest ones. It's been around for a very long time. It's you create a program in like C code and download to it, and it runs that. They also have these new ESP chips. This here is a ESP8266 in the center. This gives you lots of digital inputs and outputs, and also some analog inputs and outputs, which the Arduino does also. But what's cool about this is it actually has built-in Wi-Fi and Bluetooth right into the chip. So you see this here is the antenna for the wireless communications. They also have an advanced model of that. This one here is what they call the ESP32. So it's got a much more powerful processor. And this particular one actually has a built-in LED screen and also a long-range LoRa wireless connection. So this LoRa connection is supposed to allow you to send data up to like a kilometer away if you have proper antennas. Alright, so then they have the single board computer. The single board computer, an example of that is called the Raspberry Pi, which you may have heard of. And there's another one which we'll be using a little bit called the BeagleBone. And these ones actually use the operating system paradigm. So they run an operating system. By default, that operating system isn't a real-time operating system, but they do make real-time operating systems that you could install on them. But the nice thing about it being an operating system, as I mentioned before, you can break your control program into multiple pieces and then just start and stop individual pieces as needed. But another thing is that you can actually choose all kinds of different programming. So with those other ones, you were limited to one programming tool. Here you can have multiple different programming programs that run different programs for different tasks. So again, it's kind of pick the right tool for the right job. Certain things Python does a nice job of, but other things Python just really can't do, where you have to go to C or C++ type coding. They make very easy for wiring. They're very flexible. They use open source code, and so there's lots of examples and materials that you can make use of to get up and running very easily. So this is a picture of the Raspberry Pi. This one here is the Raspberry Pi 4. It actually has dual HDMI. These are micro HDMI connectors on here, so it can actually run dual monitors. It has a built-in NIC. It doesn't have a built-in Wi-Fi, but it does have USB ports, so you could add a Wi-Fi dongle connection. It has a board here for a camera, and then it has I/O connections over here. These are the GPIO pins for the Raspberry Pi. So if you notice here, a lot of these are just like voltage and ground connections on here. So, you need those for anything that you're doing. But then the GPIO stands for general purpose input or output. So you can kind of choose what you want to do with those. Some of them also support pulse width modulation or serial communications. One thing the Raspberry Pi does not do is an analog to digital. Now you can get little modules that would you could plug into it that do the analog to digital, but it doesn't do it natively. Now the BeagleBone is actually a combo board. It has a standard processor on it that can run an operating system, but it also contains two real-time companion processors, so you can actually run two separate real-time programs, and then you can run some more standard stuff built on top of the operating system, and you can communicate between the two very, very easily. It also has a lot more I/O. They make an industrial version of it. You know, the difference here is an industrial version implies that the soldering and the chips and the shielding and stuff was done in a way so that it's less susceptible to heat and vibration. These are the I/O pins for the BeagleBone. It actually has two 46-pin connectors, where like the Raspberry Pi only had one 40-pin, so you can see there's a lot more I/O pins here. It does have some built-in analog inputs and just a ton of general purpose I/O built into it. We can also use just a standard PC. So GP here just meant general purpose PC, personal computer, that could be running Windows or could be running Linux, or they actually make several real-time operating systems. Again, the difference is that Windows or Linux or Mac OS are not real-time. Those are the things we've seen them 100 times, where you're sitting there doing something and then all of a sudden it's just like the computer seems like it's taken forever to respond to you. But if you're running a real-time OS, you can set priority on certain tasks and be guaranteed that those are not going to take a holiday, but guarantee that they will be processed within a certain number of milliseconds. And then, of course, we have industrial controllers, generally referred to as PLCs. Okay, these are going to cost a lot more, but they are much more reliable. They're designed for the vibration and heat and that sort of thing. And in general, they're going to have 24-hour industrial support. So here's a picture of the Allen Bradley ControlLogix PLC here. So we have, this is actually the power supply on the left, and then usually the PLC itself will be the first card, and then the rest of these cards are I/O cards that you can choose what type of I/O that you want, and you can add it. These come in different size chassis, so you can choose how many, if you want only 5 cards or 10 cards or 17 different cards, you can choose how much I/O you're going to need. All right, now there are some controllers that have been created by Allen Bradley or Siemens or others that are industrial class, but they focus on the IoT or Industrial Internet of Things sort of applications. See, the issue with ControlLogix type PLC, these are basically a dedicated program. You create the program and you run it, and it will control your manufacturing process, and it does an excellent job. But what it doesn't do is it doesn't interface with the internet very well. I mean, you can send data across the network or whatever from one to the other, but if you wanted to upload stuff to the cloud, you can do it. I'm not saying you can't do it with a PLC, but it can be much more complicated, where using something like a Raspberry Pi, it's very easy to interface with the cloud and a database and things like that. So Allen Bradley and Siemens and a lot of others have developed this crossbreed sort of things that can do a little bit of both. So, for instance, Siemens, for instance, they've created a IIoT 2000 series where this is kind of an interesting device here. So again, this is industry class, so it's designed for good heat and vibration kind of stuff. But it actually has built in here, it's kind of like the BeagleBone we looked at before. It has a normal ARM processor in it that runs Linux. And then it has a separate processor, which is basically an Arduino. So it actually has an Arduino and a Linux processor on it here. So you have a real-time, the Arduino is kind of the real-time piece where you can run some real-time code. And then it has the ability to very easily pass information up to the cloud. So these here, this is the IoT 2020, cost a couple $100. All right, so if you're going to program these devices, okay, remember that a computer, meaning a controller or the processor itself, actually just runs binary or machine language. So the way it works, so here's an example of machine language. So what we have here is we have a set of instructions that are designed specifically for that processor. So if you wanted to move it over to a different processor, these instructions would have to be completely redone. And so here, the idea is we're going to add two numbers. So I have the number 10 and the number 3, which are in binary. And then I want to move number 10 into location A, which is usually referred to as a register inside of the processor. And then I'm going to move the number 3 into the second register. And then I'm going to tell the processor to add those two together. And then I'm going to move the result back out into my regular memory or RAM. So this is basically what it takes to add two numbers inside of a computer. All right. So with the first generation, we had the machine language, which was just ones and zeros. And then they went to what they called assembly language, where they created little codes. Because when you originally programmed the processors back in the very early days, you actually had to put in these ones and zeros for each instruction. So what they did with assembly language is they created these codes that said, okay, well, we're going to move into A the value 10. We're going to move into B the value 3. Then we're going to add them. Then we're going to move that result into a memory location. So this is what they called assembly language. So you had to just learn these little acronyms to do the code. Then they came up with higher level code like C, where you could define an integer, and in this case, this is what we call a pointer location, which is pointing to the memory location. We're going to store it. And then you could just do the math, 10 plus 3, and then that would be put into the memory location. And now we're really up into what we call the 4th and the 5th generations, where we can actually do these graphically. So there's a couple of different tools that we're going to be using there for some of our programming. Now, a program must be able to interact and basically do 5 different things. So these are, you have to be able to read the input data and then take the output, any kind of results, and put those into memory. You have to be able to perform calculations. you have to execute logic, and you have to be able to do iterations, right? Because one of the key points of computers is the fact that they can do these calculations over and over again. All right, so when we create a program, again, it really has to be that machine language for the processor to execute it. So then the question becomes, when do you convert it into machine language, right? Because it's got to be those ones and zeros in that machine language for it to actually be converted. So when are we going to convert it into those ones and zeros? And so you can do that either immediately as it executes, so it reads each line of code, or you can do what they say, compile the code. So if you compile the code, what you're saying is you're going to use some text language to make one of these higher level languages. But these higher level languages cannot be executed by a computer. Computers can only handle the ones and zeros. So if we compile it, it says we're going to convert it all into these ones and zeros and check it for any errors, and then we can run it whenever we want. And compiled code in general is going to run much, much faster once it's compiled. Once you go through the checks, you can compile it, and then you run it, and it's going to run very, very quickly. On the other hand, they have what they call interpreted code. With interpreted code, what you do is you give it the text-based instructions, and it reads one instruction, converts that into the machine language, executes it, then runs the next. And so the interpreted code usually it's much easier to create and test and run, but the problem with it is it tends to run much slower than compiled code. So if you pre-compile it, it's just going to run faster. Now, Java was created a while back, and the idea of Java was to kind of give us a cross between the two. And so the idea of Java was you could do some pre-testing of the code and convert it into bytecode, and then that bytecode then would be finally compiled for whichever processor. Because remember, the problem here is once you compile the code, it's only good for that particular processor. And so you can't copy the compiled code over to another machine and run it. So that was an advantage of it interpreted. If it was interpreted, you could write the program here and run it on this computer, and then you could give it to somebody else who has a different computer, but as long as they still have the interpreter, they could just run the code. So Java was actually originally designed to be a cross between those two. So when you look at the errors, you have two types of errors. Number one, you have what's called a syntax error. So each of the different programming languages provide a syntax. And so when you run the program, whether it's being interpreted or was pre-compiled, when you pre-compile it or as you're running the interpreted, the first thing it's got to do is make sure that all the rules of the language were obeyed. If they didn't, it will stop and give you a syntax error. And that syntax error then needs to be corrected before you can either compile the code or interpret the code into the machine language. But we also have logic errors. Logic errors are some sort of error with the code. So the syntax was okay, and so it compiled and executed the code, but then when we actually run the code on the computer, it does weird things. And so it's not spitting out an error saying, I don't know what to do with this instruction, but the instruction is not doing what we intended for it to do. And that's where you get, the classic software bug where something happens and you don't really know what's going on, and these can be very difficult at times to identify where they're at and how to correct them. All right, so once we have our program, we need to store that program. So we can store it into firmware, which is flash memory, or we can store it onto a hard drive or SSD drive, right? But these are long-term storage, so once we put it there, we expect it to be there whenever we want it. But for the computer to actually execute it, it has to load it up into what they call, normally we call it RAM, but that's dynamic RAM, where the like an SSD is flash RAM, or it's memory, but it's long-term storage. But it can't run the program off of these. It needs to load them into the dynamic RAM to actually execute the program. So we have two major paradigms for programming. We have what's called imperative, where the programmer gives basically step-by-step instructions of what the program's going to be. And then there's also a programming paradigm called declarative, where the programmer kind of lays out the results that you want and then you run it. So with AI coming on in play, declarative is getting much more popular because you can kind of just say, hey, this is what I want, and then the AI can then build the program. We also have what we call procedural, where you lay it out step by step, or functions. So with the functions, you have a set where, inside of a function, you basically have step 1, step 2, step 3, but then you call that function, and then you jump back, and then you call another function. And then they have object-oriented. So object-oriented is where it's kind of function-based, but the difference is that the data is incorporated with the function. All right, inside of our programs, we use a lot of different terminology. The first one that we're going to discuss here is called a variable. So a variable is going to be a value or some sort of information that we're storing in RAM. So in terms of a program, a variable is a memory location. We can have an array, which is a whole set of similar type of information. But we also have to look at the type of information or data being stored. Is it a number? Does that number have a decimal point, or is it an integer, or is it just string information? Okay, so we can have data types. If we were going to have an array, then we're going to have an integer, which will allow us to index and select one value or another value within the array. And then we have the scope. Scope refers to where the variable or the information is available. So before I was just talking about functions, so you can have a variable that is valid inside of the function, but other functions have no access to it. They don't know what that value is. Or you can have what they call like a global value, where all the functions know what that value is, and they may or may not be able to change that value depending on how things are set up, but they can at least read the value and know what it is. All right, so I already talked about this concept of RAM being dynamic RAM. So when you want to run your program, it needs to be loaded up into RAM to be executed. But a lot of times there's also what they called shared memory. And the idea with shared memory here is you can actually have two or more programs that are running and they have their own memory. Okay, so when you run a program, it gets loaded into RAM and it's given its own memory. And so if you run a different program, it's not allowed into the memory area of the first program. But you can use what's called shared memory, that you can declare a space where the two programs can pass information back and forth between them and share that information through this shared memory. When we're creating programs, usually we use what's referred to as an IDE, which stands for Integrated Development Environment. Okay. And then there's what we call the compiler. I already kind of talked about the compiler. The compiler takes your upper level language of text and converts it into the machine language for the particular processor that you're going to run on. And then we have libraries. So when you buy a compiler or an interpreter, in general, it's also going to come with a set of libraries, which are a set of functions or instructions that somebody else wrote so that we don't have to reinvent the wheel. So like this, say that you want to send something to the screen. So you want to say display an image on the screen. Well, you could go in and tell each pixel how to turn on, or you could call a function that can do that for you, and it'll save you a lot of time and effort. So we rely heavily on libraries. And then another term here is source code. So the source code is the text-based code that we wrote in our high-level language, or it might even be a graphical language. But it's our code that we created, and that code then will have to be turned into machine language to be executed. But the source code is in general easy for people to read and see what's happening and make changes to the code. All right, so here's three different examples. On the left, we have some C code or Java or JavaScript code. They all look about the same as far as their syntax, but we have a text-based code on the left. In the center, we have what's referred to as ladder logic code. This is for a PLC, a programmable logic controller. They have, when you buy the PLC, you also have to get the software for it, maybe a separate charge for that or not, depending on the PLC. But so this is kind of a graphical based thing here. And then on the right, we have a very graphical piece of code here. This is called Node-RED. And so each one of these here are nodes. And then the whole thing is called a flow, and so data will flow from a node into another node. So this node here on the left is what we call an input node, and in this case it's bringing input from across the network, and then that data is going to be passed through a function block and processed, and then it goes to an output. All right, so Node-RED is, again, it's a 5th generation IDE. It's not real time, so it'll run on Linux or it'll run on Windows. So if you have a Windows PC or a Mac, you can actually download Node-RED and run it on those. But if you have like a Raspberry Pi or a BeagleBone, it's probably already installed there and available for you to use. It's very graphical in nature, as we just saw the picture on the previous screen. And it actually runs through a web browser. So you can access it either from, like if you're using a Raspberry Pi, from the GUI on the Raspberry Pi, or from your Windows machine across the network. You just open up a web browser, connect, you have to know the IP of the device, and then you also need to know the port number. All right, so down here is the screen for Node-RED here. On the left side, they have different nodes, and you can just grab these and drag them over. So you see this blue one here is called an inject node, and I drug it over here and I changed it to a Boolean of true. So if you click on this button when it's running, it will inject a true into this connection on the right, which was actually an output sending a message to a PLC. So if I click on true, I'm sending a true or a 1 to the PLC, which according to the text here at least is supposed to tell the PLC to turn on a red light. So up here at the top here you see the address, okay, and it says 192.168.7.2 colon and then that 1880 port. Okay, so this is what we use to connect to our BeagleBone. When you plug in a BeagleBone, it'll automatically communicate through the USB cable to your PC, and have the BeagleBone will have a local IP of 192.168.7.2, which is only available through the USB cable to your PC. Alright, so we have these input nodes here. We have the inject, and then you can change the status of it. You can inject a true or a false or a string or a number. We have some other input nodes here. This is for inputting through MQTT. We have an input from a general purpose I/O pin. We can also have outputs. So notice the output here, the data is coming into the output node, but then it's leaving our program and going out. So it could be going out to the network. The green ones here are actually going out to the debug screen. But the yellow ones down here are outputting to a GPIO on a Raspberry Pi or BeagleBone. And then this one here is sending an output out across the network. So when you're working in programs, especially with like the GPIO pins and stuff, you have to pay attention to detail. So if you notice here, the one on the left has a lowercase p, and if you type that into the configuration, it will not work. It'll actually end up hanging on you. You must use a capital P. Okay, so you always have to pay attention there. Now, if it was just in a name field, it wouldn't matter. But if you're in the detail configurations, you got to pay attention to each symbol or each character. So here's the configuration screen for a GPIO of our BeagleBone. And so notice here on the blue line is pointing to the pin. This is where the capital P is extremely important. You have to have the capital P here. Now down here is just a name tag, and the name tag, it doesn't matter, but in the configuration for the actual pin, you're telling it to go to port 9, and so you have to have a capital P or it's not going to work. Alright, so here's just a simple on-off program for the BeagleBone. So we're using a BeagleBone that already has Node-RED connected here, and so we've connected to Node-RED. I grabbed a true and a false input, and I'm going to connect that to the red LED that is already wired on our BeagleBones. And so if I click on true, that true will then turn on the red light. If I click on the false, that'll turn the red light back off. Now notice down here, again, the green node here is just a debug, and so it just tells us, oh, we're at true mode or we're at false mode. Right? It's very handy to just throw these debugs on there, so if something's not working, you can kind of trace and figure out what the problem is. Okay? They also have lots of different function nodes. They have the generic function node, which means that you can actually create anything you want. It uses standard JavaScript syntax. So if you're familiar with Java or C, C++, it's really all the same. So you can pretty much figure out what's happening there. And then they also have like some dedicated nodes that do particular things and just have a configuration to them. And then there's the dashboard. So they have some here with like this light blue sort of cyanish color. And this is the dashboard library. Now, if you're using this on your own Raspberry Pi or whatever, this is probably not installed. Even though Node-RED was installed, the dashboard probably was not. So you might have to install it. But this gives you a web interface where you can program. Now, to access this, you go to your IP address :1880, but then throw in a /UI to view this screen over here. So this is the flow in the center, but to view the screen, you have to throw in the /UI. So that ends it for this video, just an overview of controllers and a little bit about programming.